The cosmos holds secrets in its deepest voids that defy everything we think we know. You are about to experience true encounters with the universe's most mysterious regions, a journey that will fundamentally change how you see the night sky. We will explore the ghostly grip of dark matter and the silent screams of black holes, stories that blur the line between established science and the sublime. By the end, you will possess a new understanding of the cosmic forces shaping reality itself. How can vast regions of nothingness influence the fate of galaxies? And what do these empty spaces whisper about the nature of time? Are you ready to question what lies beyond the edge of our understanding? Between the brilliant islands of galaxies lies an ocean of near-nothingness. We call these the cosmic voids, regions of space so empty they challenge our very understanding of the universe. They are not simply blank spots on the map, but active, dynamic elements of the cosmic web. Renowned cosmologist Laura Mersini-Houghton captured this perfectly, noting that voids are not mere emptiness. They are the negative spaces that define the structure of the cosmos. Think of the universe as a vast sponge, where galaxies cluster into dense filaments and walls, all surrounding these immense, hollow bubbles. These voids form over billions of years through gravitational evolution. Matter is pulled toward the densest regions, drawn into the great clusters, while the less dense areas are left behind, expanding and emptying out over cosmic time. The scale is almost impossible to grasp. A typical void can span hundreds of millions of light years. If you were at the center of one, the nearest galaxy would be so far away the night sky would appear utterly black, a profound and absolute darkness. The most famous example is the Boötes Void, a spherical region so colossal that our entire Milky Way galaxy would be a mere speck within it. Astronomers have found only a handful of galaxies inside its boundaries, a staggering emptiness that has puzzled scientists since its discovery. This vast nothingness is not passive. It exerts a push, an influence driven by the mysterious force we call dark energy. The emptiness within voids actually accelerates the universe's expansion, creating a gravitational repulsion that shapes the fate of everything around them. So how does the existence of such vast nothingness influence the galaxy formation we see today? It acts as a sculptor. The boundaries of voids are where galaxy formation is most active, as if the universe is building its structures at the edges of these great expanses. Understanding the void is the first step to appreciating the dark forces that shape them, forces we are only beginning to comprehend. This invisible scaffolding of the cosmos, dark matter, is the universe's greatest ghost story. It makes up over a quarter of everything that is, yet it refuses to be seen, a phantom presence whose gravity alone betrays its existence. The story of its discovery begins not in a void, but within the spiraling arms of galaxies. Astronomer Vera Rubin's meticulous observations revealed a profound mystery. Stars at the outer edges of galaxies were orbiting just as fast as those near the center. According to the laws of gravity, these far-out stars should have been flung away into the darkness. The only explanation was that the galaxies were embedded within vast, massive halos of something unseen, a substance we now call dark matter. Its gravitational grip is what holds galaxies together and sculpts the immense cosmic web, with the voids acting as the great, empty valleys between its invisible mountain ranges. So what could this mysterious substance actually be? Scientists have proposed several compelling candidates. One leading idea is WIMP, or weakly interacting massive particles. As the name suggests, these would be heavy particles that rarely interact with normal matter, passing through our world like ghosts. Another candidate is the action, a theoretical particle that is incredibly light but could exist in vast numbers. Experiments deep underground and in massive particle colliders, like the Large Hadron Collider, are hunting for these elusive entities, trying to catch a whisper of their presence. The evidence for dark matter, while indirect, is overwhelming. One of the most striking examples comes from the Boötes cluster, a system of two galaxy clusters that collided. Observations showed that the visible matter, the hot gas, was slowed and stuck in the middle of the crash. But the gravitational lensing effect, which maps the cluster's total mass, showed that most of the mass had sailed right through, a clear sign that the dominant form of matter is dark and non-interacting. This brings us back to the cosmic voids. These vast empty regions are not just empty of galaxies, they are also profound deserts of dark matter. Their gravitational push and the way they shape the universe are intrinsically linked to this missing mass. What if dark matter has properties we have not yet conceived? Could it interact with itself in strange ways within these emptinesses, creating hidden structures of its own? As we grapple with the ghostly nature of dark matter, we must also confront its strange counterpart, the force that fills these voids and pushes the universe apart. That force is dark energy, an even deeper mystery that challenges our understanding of physics itself. Dark energy is the silent, relentless force tearing the very fabric of the cosmos apart. For much of the 20th century, scientists believed the universe's expansion was slowing down, a natural consequence of gravity's pull after the Big Bang. That assumption was shattered in the late 1990s. Two independent teams, one led by Saul Perlmutter, were observing distant stellar explosions known as Type 1, a supernova. These cosmic beacons should have appeared a certain brightness if the universe was coasting or slowing. Instead, they were dimmer, much farther away than anyone predicted. The only possible explanation was staggering. The expansion of the universe was not slowing at all. It was accelerating, speeding up as if pushed by some invisible, repulsive force. Perlmutter described this discovery as a total shock, a complete overturning of our fundamental picture of the universe. This mysterious force earned the name dark energy, and calculations revealed it makes up a staggering 68% of all the energy in the cosmos. It is the dominant component of reality, and its primary effect is to push everything away from everything else. The leading theory for this bizarre force is Einstein's cosmological constant, a concept he initially proposed and then discarded. It represents a uniform energy density intrinsic to empty space itself. Think of the vacuum of space not as true nothingness, but as a seething, energetic field that generates a kind of negative pressure, forcing the universe to expand faster and faster over time. This has a profound effect on the cosmic voids we explored earlier. Dark energy acts upon these empty regions most effectively, with very little matter inside to provide a counteracting gravitational pull. The voids themselves are expanding at an ever-increasing rate. They are growing in volume, stretching their boundaries and becoming even emptier over billions of years. This relentless push is what counteracts gravity on the very largest scales. While gravity works to pull matter together into clusters and filaments, dark energy works to tear them apart, creating a cosmic tug-of-war that dark energy is decisively winning. Key evidence for this cosmic recipe comes from the Planck satellite, which mapped the faint afterglow of the Big Bang, the cosmic microwave background. Its precise measurements confirmed the exact balance of ingredients in our universe. Just 5% normal matter, around 27% dark matter, and 68% dark energy. This balance dictates the ultimate fate of everything. If dark energy continues to accelerate the expansion, as all evidence suggests, the universe may be headed for a big freeze. Galaxies will be pulled so far apart that the sky will go dark, and the cosmos will become an immense, cold, and lonely void. This force is perhaps the greatest mystery in all of science. Could dark energy be a manifestation of a deeper, unknown physics that we are only beginning to glimpse? To understand its true nature, we must turn to the places where gravity becomes an absolute tyrant, where the fabric of spacetime is torn asunder. We must journey to the edge of a black hole. At the boundary of a black hole, the universe sets a point of no return called the event horizon. This is not a physical surface you could touch, but a mathematical threshold in spacetime, a one-way door from which nothing, not even a single photon of light, can ever come back. Crossing this line means that the pull of gravity becomes absolute, warping the paths of light and matter so severely that every future leads inward, toward the crushing center. This creates a perfect void in our observations, a black sphere against the cosmos from which no information can ever reach us. Black holes come in different terrifying scales. Stellar mass black holes form from the collapsed cores of massive stars, while supermassive beasts, weighing millions or even billions of times our sun's mass, lurk at the hearts of galaxies. Both represent places where our current laws of physics simply break down. The core of a black hole is thought to be the singularity, a point of infinite density where the fabric of spacetime itself is torn. Surrounding the singularity of a spinning black hole is the ergosphere, a region where spacetime is dragged around so violently that nothing can remain stationary. It is like being caught in a cosmic whirlpool from which you cannot escape. For decades, these objects were purely theoretical, but we can now detect them through their dramatic effects on their surroundings. As nearby gas and dust are pulled into orbit, they form a superheated accretion disk that glows with intense radiation, outlining the black hole's dark shadow. The collision of two black holes sends ripples through spacetime itself, gravitational waves that we can now detect with observatories like LIGO and Virgo. A monumental achievement was the first direct image of a black hole's shadow at the heart of the galaxy M87, captured by the Event Horizon Telescope, a global network of observatories working in perfect synchrony. This fiery ring of light confirmed the predictions of Einstein's theory on an unimaginable scale. It was a triumph of international collaboration, giving us a glimpse of the event horizon itself. Yet for all we have learned, black holes hold profound secrets. Stephen Hawking's revolutionary work showed that black holes are not completely black. Due to strange quantum effects at the very edge of the event horizon, they can slowly leak radiation and evaporate over trillions of years. This Hawking radiation creates a deep puzzle known as the information paradox. According to quantum mechanics, information about what falls into a black hole can never be truly destroyed. But if the black hole evaporates, what happens to that information? Is it lost forever, violating a fundamental law of physics? Or is it somehow encoded on the event horizon itself, a permanent record of everything it has consumed? This question strikes at the very heart of our understanding of reality, forcing us to reconcile gravity with the quantum world. As we ponder the ultimate fate of information within these dark voids, our journey leads us to another cosmic extreme, where matter is compressed not into a black hole, but into a star of impossible density. The death of a massive star forges one of the most bizarre objects in the cosmos. When a star many times heavier than our Sun exhausts its nuclear fuel, its core collapses in a cataclysmic supernova explosion. The outer layers are blasted into space, while the core is crushed under its own immense gravity. What remains is a neutron star, a city-sized object containing more mass than our entire Sun, a density so extreme that a single teaspoon of its material would weigh billions of tons. This matter is compressed into a state we cannot replicate anywhere on Earth, a sea of neutrons packed so tightly that the very atoms themselves have been obliterated. These stellar cinders often reveal themselves as pulsars, cosmic lighthouses that sweep the universe with precise, rhythmic beams of radiation. The discovery of the first pulsar is a story of brilliant observation. In 1967, a young graduate student named Jocelyn Bell Burnell noticed a strange, repeating signal in her radio telescope data. It was so regular, pulsing exactly every 1.337 seconds, that she and her supervisor half-jokingly labeled it LGM-1 for Little Green Men. It was, of course, not aliens, but the first observed pulsar, a rapidly spinning neutron star. Bell Burnell later reflected on the profound humility of science, noting how this tiny, rhythmic signal opened an entirely new field of astronomy. The clock-like precision of these pulses is not just a curiosity, it is a powerful tool. The timing of pulsar signals is so reliable that scientists use them as navigational beacons for theoretical spacecraft, and to create a galactic positioning system. Their incredible stability also allows us to test the fabric of spacetime itself. The most famous example is the Hulse-Taylor binary pulsar, a system of two neutron stars orbiting each other. By meticulously tracking their pulses for decades, astronomers noticed their orbit was slowly decaying. The two massive objects were losing energy, spiraling inward in a way that perfectly matched the predictions of Einstein's general relativity. They were emitting gravitational waves, ripples in spacetime, providing the first indirect evidence for a phenomenon that would later be directly detected. Yet neutron stars are not always perfectly predictable. They occasionally experience starquakes, sudden shifts in their crust that cause a glitch, a tiny but measurable change in their spin rate. Even more extreme are the magnetars, neutron stars with magnetic fields so powerful they could erase a credit card from halfway to the moon. When these magnetic fields suddenly shift, they can release immense flares of energy, gamma-ray bursts that can temporarily outshine entire galaxies and disrupt satellites around Earth. How does matter behave when it is squeezed into a state with no empty space left? These stellar remnants are natural laboratories, pushing the very laws of nuclear physics to their breaking point and challenging our models of the fundamental forces. The very existence of neutron stars is a direct consequence of the most violent explosions in the universe, the supernova that seed the cosmos with the elements of life. The death of a star is a violent act of cosmic creation. A supernova explosion unleashes more energy in a few weeks than our Sun will emit over its entire 10 billion-year lifetime, briefly outshining every other star in its host galaxy combined. These events are not merely spectacular. They are the primary engines of cosmic recycling, forging the heavy elements that make up our world and our very bodies. The term itself was coined by the brilliant and often contentious astronomer Fritz Zwicky. In the 1930s, he recognized that these were not new stars, but the catastrophic deaths of old ones, and he proposed they were the birthplaces of neutron stars. He also identified their vital use as standard candles, because a certain class of supernova, type 1a, always explodes with roughly the same peak brightness. Astronomers can measure their apparent dimness to calculate vast distances across the universe, a technique that led directly to the shocking discovery of dark energy. There are two primary paths to this stellar annihilation. The first is the core collapse supernova. This is the fate of a star at least 8 times more massive than our Sun. When its core can no longer support fusion, it collapses in less than a second. The outer layers crash down and then rebound in a titanic shockwave, blasting the star apart and leaving behind either a neutron star or, for the most massive progenitors, a black hole. The second type, type 1a, begins with a white dwarf in a binary system. This Earth-sized remnant of a Sun-like star is incredibly dense. If it siphons enough material from its companion, it can be pushed over a critical mass threshold, reigniting runaway nuclear fusion in its carbon core that tears the entire white dwarf to pieces. The aftermath of these explosions is both destructive and stunningly beautiful. The ejected material, now rich with newly forged elements like iron, oxygen, and silicon, expands at thousands of kilometers per second, creating an immense shockwave that plows into the surrounding interstellar gas. This cosmic debris field, glowing for thousands of years, forms a supernova remnant. The most famous is the Crab Nebula, the expanding wreckage of a star whose death was meticulously recorded by Chinese and other astronomers in the year 1054. They observed a guest star visible even in the daytime for weeks, a silent testament to humanity's long watch of the heavens. Every time you breathe in oxygen or see the gleam of a gold ring, you are witnessing the legacy of a long-dead star. These explosions seeded the galaxy with the raw materials for planets, oceans, and life itself. But their power also poses a hypothetical threat. A supernova occurring within a few dozen light-years of Earth would bathe our planet in dangerous radiation, potentially triggering mass extinctions and crippling our electronic infrastructure. While no such nearby star is poised to explode, it is a humbling reminder of our place in a dynamic and sometimes dangerous cosmos. This violent beauty, however, is sometimes just the beginning. The collapse of a massive star can also send a different kind of message across the universe, not a flash of light, but a ripple in the fabric of space-time itself. Deep within the cosmic static, a millisecond burst of radio waves can outshine an entire galaxy. These are fast radio bursts, or FRB, some of the most fleeting and energetic signals ever detected. They arrive without warning, a blast of radio noise that travels for millions or even billions of years across the void, only to vanish in an instant, leaving behind a profound mystery. Their discovery was almost lost in the data. Astronomer Duncan Lorimer and his team were analyzing archival observations from a radio telescope in 2007, when they found a single, powerful burst that had been recorded 6 years earlier. It was so brilliant and so brief that Lorimer initially wondered if it was an instrumentation error. He later described the moment as a combination of excitement and caution, knowing they had found something truly new and unexplained. The energy released in that mere 5 milliseconds was staggering, equivalent to the total output of our Sun over 80 days. Since that first discovery, hundreds more of these bursts have been detected, primarily by advanced radio telescopes like CHIME in Canada, which scans the entire northern sky each day. These signals are not all the same. Some are one-off events, a single explosive shout into the darkness. Others are repeaters like the famous FRB 1211-2, which sends out multiple bursts from the same location, a dwarf galaxy 3 billion light-years away. This repeating behavior was a major clue, ruling out cataclysmic, one-time events like the merger of 2 neutron stars for at least some of the bursts. So what could possibly create such immense energy in such a short time? The prime suspect for many repeating FRBs is the magnetar, a type of neutron star with a magnetic field so powerful it could strip the information from every credit card on Earth from halfway across the galaxy. Theorists suggest that starquakes on the surfaces of these magnetars, or sudden rearrangements of their impossibly strong magnetic fields, could generate these intense radio flashes. Yet even this compelling explanation does not fit every case, leaving the door open for more exotic possibilities, including highly speculative ideas like powerful beams from advanced alien civilizations. Beyond the question of their source, these bursts are incredibly useful tools. As an FRB travels through the sparse material between galaxies, its different radio frequencies are slowed down by ever so slightly different amounts. This effect, called the dispersion measure, creates a telltale smear in the signal. By measuring this smear, astronomers can calculate the total amount of ionized material the burst has passed through, effectively using the FRB as a probe to weigh the universe's missing normal matter, the baryons that theories predict should exist but have been notoriously difficult to find. Each burst is like a single, brilliant flash of lightning in a fog, illuminating the structure of the cosmic web for a fleeting moment. Are we listening to the natural death cries of hypermagnetic stars? Or could we be intercepting the encoded transmissions of an intelligence beyond our own? As we search the skies for these cryptic messages, We are also bombarded by another type of messenger from the void, one made not of radio waves, but of atomic nuclei traveling at nearly the speed of light. These high-energy messengers from the void are not made of light, but of matter itself. Subatomic particles, often single protons or atomic nuclei, race across the universe at nearly the speed of light. They carry energies so immense they are millions of times more powerful than anything produced in the most advanced particle colliders on Earth. We call these ultra-high-energy cosmic rays, and their existence points to cosmic engines of almost unimaginable violence. For over a century, scientists have known that our planet is constantly bombarded by cosmic rays, but the ultra-high-energy ones are exceptionally rare. Detecting them requires an observatory of epic scale. The Pierre Auger Observatory in Argentina spans an area of over 3,000 square kilometers, an array of 1,600 water tanks separated by over a mile, all watching the sky for the telltale sign of a single particle's death. When one of these ultra-high-energy particles strikes the top of our atmosphere, it does not reach the ground. Instead, it collides with an air molecule, triggering a cascade of secondary particles that fan out in an extensive air shower, a sprawling umbrella of energy that can be detected across the entire observatory site. By studying the pattern and timing of this shower as it rains down, scientists can work backwards to calculate the original particle's energy and its incoming direction. Yet this is where the mystery deepens. The paths of these charged particles are not straight lines. As they travel for millions of light years, they are bent and twisted by the weak but pervasive magnetic fields that fill the space between galaxies. It is like trying to trace a single raindrop back to its cloud in the middle of a hurricane. The particle that arrives at our detector points not to its true source, but to the last curve in its long, winding journey. This magnetic deflection makes pinpointing their origins one of the greatest challenges in modern astrophysics. The very existence of these particles also poses a theoretical puzzle known as the GZK cutoff. Two physicists, Greisen, Zatsepin, and Kuzmin, predicted that the most energetic cosmic rays should not be able to travel very far. They would interact with the photons of the cosmic microwave background, the leftover glow from the Big Bang. Over long distances, these interactions would sap their energy, effectively creating a speed limit for particles arriving from distant corners of the universe. The fact that we do detect particles with energies beyond this predicted cutoff means they must come from relatively nearby in cosmic terms, within a few 100 million light years, making the hunt for their local sources even more urgent. So what cosmic catastrophes can possibly serve as these natural particle accelerators? The suspects are the usual titans of cosmic violence: active galactic nuclei, where matter spirals into a supermassive black hole, can eject jets of plasma at relativistic speeds. Gamma-ray bursts, the most energetic explosions since the Big Bang, could also be capable of this immense acceleration. The enigma was perfectly captured by the detection of a single particle in 1991, an event so shocking it was dubbed the "Oh my God" particle. It was a single proton, but it carried the kinetic energy of a well-thrown baseball, all compressed into a subatomic speck. It was moving so fast that, due to the effects of special relativity, only a few other particles in the entire universe could have outpaced it. The cosmic engine that created it remains completely unknown. This is where the new era of multi-messenger astronomy becomes essential. By correlating the arrival of an ultra-high-energy cosmic ray with other signals from the same patch of sky, like a neutrino detection or a gamma-ray flare, we might finally pinpoint the source. These particles are the atomic bullets fired from the universe's most extreme events, and by catching them, we are reading a message written in the language of pure energy. What do these invisible bullets tell us about the magnetic highways that guide them across the vast cosmic voids? This invisible architecture of magnetic force weaves through the entire galaxy, a ghostly web guiding the very flow of matter and energy. Generated by vast dynamo processes within the churning plasma between stars, these fields are the silent shapers of cosmic evolution. We cannot see them directly, but their presence is betrayed by the light they influence. When starlight passes through clouds of magnetically aligned dust, it becomes polarized, its waves vibrating in a preferred direction. Even more telling is synchrotron radiation, the faint glow emitted by electrons spiraling at nearly the speed of light along these invisible magnetic lines. Astronomer Rainer Beck has spent decades mapping these fields, noting their profound influence on the most fundamental cosmic processes. They can provide a supporting pressure that slows the collapse of giant gas clouds, subtly regulating the birth rate of new stars. They also act as immense, labyrinthine channels for the ultra-high-energy cosmic rays we discussed, guiding these atomic bullets across the galaxy and confining them for millions of years. To map this invisible scaffold, scientists use a technique called Faraday rotation. As polarized light travels through a magnetized plasma, its direction of polarization slowly twists. By measuring this rotation in the light from distant pulsars and galaxies, astronomers can work backwards to calculate the strength and direction of the magnetic fields it passed through. These fields are not uniform. They vary dramatically from the ordered spiral arms, where they align with the galaxy's structure, to the turbulent halos that surround the galactic disk, where magnetic loops and bubbles rise and fall. Our own Milky Way provides the clearest laboratory. Observations of hundreds of pulsars have revealed our galaxy's magnetic skeleton in exquisite detail, a complex tapestry of both large-scale, ordered fields and smaller, chaotic, turbulent ones. This magnetic structure provides a crucial pressure that helps maintain the stability of the entire galactic disk, preventing it from flying apart or collapsing inward. But what of the cosmic voids, those immense deserts of space? Here, magnetic fields are believed to be far weaker and more primordial, perhaps relics from the universe's infancy. Studying these faint void fields could reveal the universe's magnetic history, telling us if magnetism is a fundamental property of the cosmos or one that was forged later in the hearts of galaxies. This grand magnetic tapestry extends beyond single galaxies, connecting them across the vast expanse of space and setting the stage for the largest gravitationally bound structures in existence. Our galaxy is not drifting aimlessly through the void. It is caught in a current, a vast river of galaxies all flowing toward a single, unseen point in the darkness. This mysterious destination is known as the Great Attractor, a gravitational anomaly of staggering proportions hidden behind the thick dust and stars of our own Milky Way's central plane. For decades, this region was a profound blind spot, a zone of avoidance that our optical telescopes could not penetrate. We knew something was there because we could feel its pull. By meticulously mapping the motions of thousands of galaxies, astronomers noticed our local group, and countless others were moving with a peculiar velocity, a deviation from the universe's smooth expansion that could only be explained by a colossal concentration of mass tugging at us from the shadows. This was not just our galaxy wandering, but a bulk flow, a coordinated movement of an immense volume of space, all drawn toward the same gravitational well. The discovery hinged on distinguishing this cosmic current from the general expansion of the universe. Think of it like a leaf floating on a wide, smoothly flowing river. If the leaf suddenly picks up speed, you know a powerful whirlpool is pulling it from below. The Great Attractor is that whirlpool, an overdensity of mass so vast it warps the motion of everything around it. The true nature of this hidden giant began to emerge with infrared surveys like the 2-micron all-sky survey, or 2MASS. Infrared light slips through the cosmic dust that blocks visible light, allowing us to peer into the zone of avoidance for the first time. These observations, combined with radio surveys, revealed that the Great Attractor is not a single, incomprehensible object. It is the gravitational core of our home supercluster, a structure we now call Laniakea, a Hawaiian word meaning immense heaven. Laniakea spans over 500 million light-years, a continent of galaxies, and we are on its distant outskirts, flowing toward its dense center. Yet the story grows more complex. The Great Attractor itself seems to be moving, pulled toward an even more massive structure known as the Shapley supercluster, located hundreds of millions of light-years beyond. This creates a cosmic tug-of-war on a scale that defies human intuition, with multiple gravitational giants vying for influence across the vast web. What provides the immense gravity for these flows? The answer lies in the unseen architecture of the cosmos. The Great Attractor's pull is not generated by the visible galaxies alone. Its true strength comes from a deep well of dark matter, the invisible scaffolding that holds these vast structures together and dictates their gravitational influence. The motion of our entire galaxy is a testament to the power of this dark framework. So what other hidden mass concentrations are out there, silently guiding the grand dance of the cosmos? As we ponder these immense flows, we must also turn our attention to the spaces between them, the great cosmic voids where the fabric of reality is stretched to its absolute limit. Within these vast cosmic bubbles, galaxies are not entirely absent. They exist as isolated island universes, adrift in an ocean of near-nothingness. These are the void galaxies, and their lonely existence makes them profoundly different from their cousins in the crowded galactic clusters. Freed from the gravitational tides and violent encounters of dense environments, these galaxies evolve in slow, quiet isolation. They often retain more of their primordial gas, the raw fuel for star formation, leading to a population of bluer, younger, and more irregularly shaped stellar systems. They are cosmic time capsules, preserving a quieter, more gentle mode of galaxy evolution that has largely ended elsewhere in the universe. Rien van de Weygert, a leading researcher on cosmic voids, describes them as the universe's underdogs, offering a unique view into how galaxies form when left to their own devices. The emptiness itself is not uniform. Voids exist in a hierarchy of scales, from small mini-voids that form between galactic filaments to the staggering supervoids that can span hundreds of millions of light-years. Our observations from massive surveys like the Sloan Digital Sky Survey have painstakingly mapped the intricate boundaries of these empty regions, tracing the delicate filigree of the cosmic web that contains them. One of our nearest cosmic neighbors is the Lynx Cancer Void, a sprawling emptiness that provides a perfect local laboratory. Within it, astronomers have identified a handful of these isolated void galaxies, each one a testament to star formation persevering in the most meager of environments. But the true power of these voids lies not in what they contain, but in what they do. Their profound underdensity makes them ideal testing grounds for dark energy. With so little matter inside to provide a counteracting gravitational pull, the repulsive force of dark energy acts most effectively. As van de Weygert explains, voids expand faster than the universe's average, their boundaries stretching outward at an ever-increasing rate. This accelerated growth provides a direct measure of dark energy's strength and its effect on the fabric of spacetime. Even the faint afterglow of the Big Bang, the cosmic microwave background radiation, bears the imprint of these great emptinesses. As light from this primordial glow passes through a supervoid, it loses a tiny amount of energy, a subtle cold spot in the microwave sky that serves as a permanent record of the void's existence. Could these growing bubbles of nothingness be the ultimate key to unraveling dark energy? Their relentless expansion offers one of the most direct tests for our cosmological models, a pure experiment unfolding on a billion-year scale. They challenge our very perception of reality, forcing us to see that emptiness is not passive, but an active, dominant force in the cosmic drama. The origin of these vast regions of nothing may itself be traced back to the very smallest of beginnings, to the quantum fluctuations that first stirred in the fiery instant of creation. The seeds of our entire cosmic web were planted in the first fleeting moments of existence, born from a quantum chaos almost too small to comprehend. In that searing hot beginning, the universe was a roiling sea of energy where particles and forces flickered in and out of existence, a storm of quantum fluctuations at the smallest possible scale. These were not mere jitters, but the very blueprint for everything to come. The theory of cosmic inflation, pioneered by physicist Alan Guth, proposes that an unimaginably rapid expansion of space itself occurred in the first fraction of a second. This inflationary burst stretched those tiny quantum ripples across the cosmos, magnifying them into the faint density variations that would one day become the great walls of galaxies and the immense, empty valleys of the cosmic voids. Guth described this process as the ultimate free lunch, where the microscopic quirks of the quantum world were blown up to become the largest structures we can observe. The most compelling evidence for this quantum origin story is written in the sky, in the faint afterglow of the Big Bang. The Planck satellite's exquisitely detailed map of the cosmic microwave background reveals tiny temperature differences, anisotropies that appear as slightly warmer and cooler spots. These spots are not random. Their pattern and size distribution match the predictions of inflation with stunning precision, a fossilized imprint of those primordial quantum fluctuations. The warmer spots correspond to regions of slightly higher density, the future homes of galaxy clusters. The cooler spots are the seeds of the great voids, the troughs in that initial wave where less matter would eventually gather. This cosmic fingerprint is our most direct link back to the universe's first instance. The hunt for even deeper evidence continues, focusing on a specific signature inflation would have left behind: primordial gravitational waves. These are not waves in space, but ripples in the fabric of spacetime itself, generated by the violent expansion of the inflationary epoch. A key prediction is that these waves would have polarized the cosmic microwave background light in a unique swirling pattern, known as B-mode polarization. The BICEP and Keck array collaborations, using telescopes at the South Pole, are searching for this faint signal in the frigid, dry polar air. Their initial announcement of a possible detection in 2014 was a moment of high excitement, though later analysis showed it was likely due to interstellar dust. The quest continues, as this signal would provide a direct window into the energy scales of inflation, telling us what drove the universe's explosive birth. This line of thinking leads to a truly mind-bending possibility. If inflation could happen once, what if it never truly stopped? The concept of eternal inflation suggests that our entire observable universe is just one bubble in a vast, ever-growing multiverse. Inflation ends in our local region, allowing for the formation of stars and galaxies, but continues elsewhere, endlessly spawning new cosmic bubbles with potentially different physical laws. Our cosmos, with its specific balance of forces that allows for our existence, could be just one fortunate island in an infinite cosmic ocean. The voids we see today, those vast expanding bubbles of nothingness, are perhaps the closest analogues we have within our own universe to the greater nothingness that may separate us from other cosmic realms in the multiverse. This quantum origin story, from the tiniest jitters to the largest structures, is inextricably linked to another cosmic hum, the background of gravitational waves that ripple through the cosmos from countless violent events. A new sense is opening for astronomy, allowing us to hear the universe breathe. When massive objects like black holes spiral into each other, they do not create sound in the void, but they do shake the very fabric of spacetime, sending out ripples known as gravitational waves. For a century, these waves were a ghostly prediction of Einstein's theory of general relativity, a mathematical certainty waiting for technology to catch up. Nobel laureate Kip Thorne, one of the visionary founders of the LIGO project, described the detection as opening a new window on the universe, one where we are no longer solely reliant on light. We are now listening to the cosmos. The instruments that achieved this seemingly impossible feat are marvels of precision, known as laser interferometers. Facilities like LIGO in the United States and Virgo in Italy work by splitting a laser beam and sending the two halves down long, perpendicular vacuum tunnels several kilometers in length. The beams reflect off mirrors and are recombined. Under normal conditions, the light waves cancel each other out. But when a gravitational wave passes through the Earth, it minutely stretches space in one direction and compresses it in the other, changing the length of the arms by a distance thousands of times smaller than a single proton. This tiny shift creates a fleeting, telltale flicker in the laser light, a signature of cosmic violence occurring millions or even billions of light years away. The sources of these space-time shudders are the most energetic events imaginable. The first direct detection in 2015 was the merger of two black holes, an event so powerful it briefly radiated more energy than all the stars in the observable universe combined. Since then, dozens of collisions between black holes and neutron stars have been recorded, each one a unique crash that we can now hear. The true power of this new sense was demonstrated spectacularly in August 2017 with an event designated GW170817. For the first time, gravitational wave observatories detected the spiral dance of two neutron stars. Just seconds later, space-based gamma-ray telescopes saw a flash from the same patch of sky, and ground-based observatories swung into action to capture the fading afterglow. This multi-messenger event was a scientific bonanza. The observations confirmed that such mergers are the cosmic forges where heavy elements like gold, platinum, and uranium are created, solving a long-standing mystery about the origin of the precious metals we find on Earth. But the ambition of gravitational wave science stretches even further. Beyond these distinct chirps from individual collisions, scientists are hunting for a faint, persistent hum, a stochastic background of gravitational waves. This would be the combined rumble from countless merging supermassive black holes throughout cosmic history, and perhaps even a fossil echo from the universe's birth. The primordial gravitational waves generated by cosmic inflation would have left a permanent, if incredibly faint, imprint on the cosmos. To detect this deepest of all cosmic sounds, we must go to space. Future missions like the Laser Interferometer Space Antenna, or LISA, will consist of 3 spacecraft flying in a precise triangular formation millions of kilometers apart, creating a detector sensitive to the low-frequency waves that are impossible to measure on Earth. This would allow us to listen to the mergers of the very first black holes and probe the conditions of the Big Bang itself. These ripples in spacetime are the final messengers, carrying secrets from the earliest moments and guiding us back to the oldest light we can see, the cosmic microwave background. This ancient light is the oldest photograph of our universe, a snapshot taken when it was just 380,000 years old. Before this moment, the cosmos was a searing, opaque fog of plasma, too hot for light to travel freely. But as it expanded and cooled, a monumental shift occurred. Electrons combined with protons to form the first hydrogen atoms in an event called recombination. Suddenly, the universe became transparent, and those trapped photons were set free on a journey that continues to this day. We see this as the cosmic microwave background, a nearly uniform glow that bathes all of space. The Planck satellite has mapped this afterglow with breathtaking precision, revealing a universe that is 99.9% smooth. But it is the remaining 0.1%, the tiny temperature fluctuations, that hold the universe's deepest secrets. These minute-hot and cold spots are the fossilized imprints of the primordial density variations from the inflationary epoch. The slightly denser regions, seen as warmer areas in the map, would eventually collapse under gravity to form galaxy clusters. The less dense regions, the cold spots, became the seeds of the great cosmic voids. This blueprint, encoded in this ancient light, perfectly supports our standard model of cosmology, known as lambda CDM. Yet within this spectacular conformation lie strange and persistent anomalies that refuse to fit the expected pattern. One of the most significant is a puzzling alignment, sometimes called the axis of evil. According to the standard model, the fluctuations in the cosmic microwave background should be randomly distributed across the sky. But several large-scale features, including the quadrupole and octupole moments, appear to be aligned with each other and with the geometry of our solar system, a correlation that should be impossibly unlikely. It is as if the universe has a preferred direction, challenging the foundational principle that it should look the same in every direction. Another profound oddity is the dipole asymmetry. The sky is not perfectly even. One hemisphere is very slightly warmer than the other, an effect we mostly attribute to our motion through space. But the Planck data suggests that the intrinsic fluctuations themselves might be slightly stronger on one side of the universe than the other, a potential sign that inflation did not proceed uniformly everywhere. Then there is the famous cold spot, a vast and unusually cool region in the southern galactic hemisphere. One compelling explanation is that it is a shadow cast by an immense supervoid, a cosmic emptiness so vast that photons lose energy climbing out of its shallow gravitational well. Yet surveys have struggled to find a void large enough to explain its profound coldness. This has led to more exotic theories, including the speculative idea that it could be a bruise from a collision with another universe bubble in the multiverse. Do these anomalies mean our cosmological model is broken? Or are they simply statistical flukes in a universe that is, after all, a single unique realization? The Planck team itself has rigorously analyzed these features, confirming they are real and not instrumental errors, but stopping short of claiming they require new physics. The mystery pushes at the very limits of our knowledge, forcing us to ask if we are seeing the limits of our model or the first hints of a grander cosmic structure, perhaps shaped by a pre-inflationary universe or a complex topological shape to all of spacetime. This primordial light does more than just reveal our past. Its subtle patterns are intimately tied to the dark energy that dominates our future. The same map that shows us the infant universe also precisely measures the cosmic ingredients that dictate its ultimate fate, a fate of expansion driven by that mysterious repulsive force. The cosmic microwave background is our most direct link to the beginning, and its lingering whispers suggest our story is far from complete. The relentless expansion driven by dark energy points toward a final, chilling destination. If this acceleration continues unchecked, the universe will not end in fire or ice, but in a profound and absolute stillness known as the Big Freeze. This is the leading theory for our cosmic fate, a direct consequence of dark energy's dominance overwhelming the collective gravitational pull of all matter. Cosmologist Lawrence Krauss paints a stark picture of this future, describing a universe evolving inevitably toward a state of maximum entropy, where all energy is evenly distributed and no work can be done. It is the ultimate heat death. The timeline for this decay is almost beyond human comprehension. In about 1 trillion years, the last stars will have burned out, leaving the cosmos filled with the cooling remnants of white dwarfs and neutron stars. Galaxies, their gravitational bonds severed by the accelerating expansion, will have long since receded from one another's view, each an isolated island in an ever-widening sea of nothingness. Over trillions upon trillions of more years, even these stellar corpses will vanish. Black holes, once thought to be eternal, will slowly evaporate through Hawking radiation, releasing their final whispers of energy into the void. Some theories suggest that even the very fabric of matter may not be permanent, with protons themselves decaying over staggering timescales. What remains is a universe of isolated particles, so diffuse that encounters become impossibly rare, and the temperature approaches absolute zero. This is not the only potential end, however. A more violent alternative is the Big Rip. In this scenario, dark energy does not just accelerate expansion, but grows in strength over time. If it becomes dominant enough, it would not just separate galaxies but tear them apart. Later, it would rip stars from their galaxies and planets from their stars. In the final moments, it would overcome the forces holding atoms together, shredding all matter into a mist of fundamental particles. While current data does not strongly support this, it remains a haunting possibility. The cosmic voids we have explored are the vanguard of this bleak future. They will continue to grow, merging with one another until the entire observable universe becomes one immense void. The great cosmic web, with its brilliant filaments and clusters, will be a distant memory. Could new physics offer an escape from this destiny? What if dark energy is not a constant force, but one that decays or changes over time, potentially allowing for a new phase of cosmic activity? For now, the evidence points toward a cold, dark, and silent eternity. This ultimate fate, dictated by the mysterious properties of dark energy and the geometry of space, forces us to confront a profound irony. The very cosmic forces that lead to this frozen end are the same ones that, in our brief window of cosmic time, created the precise conditions for stars, planets, and life itself to arise. The gold in a wedding ring and the uranium fueling power plants share a violent cosmic origin. These heavy elements are not forged in the calm hearts of living stars, but in the most extreme events the universe can muster. Their creation hinges on a specific nuclear alchemy known as the rapid neutron capture process, or the R process. This requires an environment of almost unimaginable density and temperature, where atomic nuclei are bombarded by a flood of free neutrons in a fraction of a second. Before the nucleus has time to decay, it rapidly captures neutron after neutron, building up weightier and weightier elements, all the way to gold, platinum, and uranium. For decades, the location of these cosmic forges was one of astronomy's great puzzles. Theorists proposed two likely sites: the cataclysmic collapses of massive stars in supernova, and the violent mergers of neutron stars. The breakthrough came with the first multi-messenger observation of a neutron star merger, an event known as GW 170817. Astronomer Enrico Ramirez Ruiz described it as a watershed moment, where gravitational waves announced the collision and telescopes then saw the glowing, expanding debris cloud rich with newly synthesized heavy elements. The data confirmed that a single such merger can forge an amount of gold equal to the mass of several planet Earths, scattering these precious metals into the surrounding galaxy. This R process is distinct from the slower S process, which occurs over thousands of years in the interiors of aging, giant stars. That slower process creates different elements, like strontium and barium, but it cannot produce the very heaviest elements we find on Earth. Each pathway contributes to the galactic inventory, with the R process responsible for about half of all elements heavier than iron. Core collapse supernova also play a vital role in cosmic chemistry, producing the lighter, heavy elements essential for life. The oxygen we breathe, the carbon in our bodies, and the silicon in rocks were all synthesized in the fiery deaths of massive stars, and then blasted into space by the ensuing explosion. This stellar debris mixes with primordial hydrogen and helium in vast interstellar clouds, eventually collapsing to form new generations of stars and planets. Our own solar system formed from a cloud that had been enriched by countless such stellar deaths over billions of years. Every element in our bodies and our world is a piece of stellar shrapnel, a relic of ancient cosmic violence. This history of chemical enrichment is written in the light of every galaxy, but the story may be different in the vast cosmic voids. In those sparse, isolated environments, where galaxy interactions and stellar deaths are far less frequent, the abundance of heavy elements is likely significantly lower. The void galaxies may be chemically primitive, representing an earlier, less processed state of the universe. Their composition a quiet echo of a time before the cosmos was fully seeded with the elements of complexity. If the stuff of planets and life is born from stellar cataclysms, its very existence hinges on a deeper, more fundamental mystery. Why is our universe made almost entirely of matter, when the laws of physics seem to demand a perfect balance with its mysterious opposite, antimatter? Our universe exists only because of a broken symmetry. The Big Bang should have created equal amounts of matter and antimatter, two opposing kinds of stuff that annihilate each other instantly upon contact, leaving behind nothing but pure energy. If nature were perfectly fair, all the matter and antimatter would have mutually destroyed one another, and the cosmos would be a featureless sea of radiation, empty of stars, planets, or life. The simple, staggering fact that we are here means the initial symmetry was profoundly violated. Something tipped the scales, allowing one particle of matter to survive for every billion annihilations. This matter-antimatter asymmetry is one of the most profound puzzles in all of science. Nobel laureate James Cronin, who co-discovered a key piece of this puzzle known as CP violation, reflected that they were not looking for anything so fundamental. They were simply studying the behavior of strange particles called kaons, and stumbled upon a tiny crack in the mirror of reality. He noted that even a small effect can have immense consequences for the universe. This CP violation describes a tiny but crucial difference in how particles and their antimatter counterparts decay. It is as if a law of physics works slightly differently for matter than it does for its mirror image made of antimatter. This tiny bias, repeated across the hot, dense early universe, could have been the seed that led to the overwhelming dominance of matter we see today. But for this to work, the universe needed to satisfy a set of criteria first outlined by physicist Andrei Sakharov. These Sakharov conditions provide the recipe for creating a matter-dominated cosmos. First, the processes at work must violate baryon number, meaning they can change the total amount of matter in the universe, a rule that standard particle physics says should be conserved. Second, there must be both C and CP violation, breaking the symmetries between matter and antimatter. And third, these processes must occur out of thermal equilibrium, away from the smooth, uniform heat of the primordial fireball, to prevent the nascent matter from being immediately annihilated back out of existence. The search for physics that fulfills these conditions drives experiments at the largest particle colliders, like CERN. Scientists are hunting for any slight difference between the behavior of matter and antimatter, any deviation that could explain our existence. The evidence from the cosmos itself is equally telling. If large regions of antimatter existed, we would see a constant, brilliant glow of gamma rays at the boundaries where they met normal matter, as the two annihilated. Our most sensitive telescopes have scanned the sky and found no such evidence. Furthermore, cosmic ray detectors find a striking absence of anti-nuclei, like anti-helium, which would be a clear sign of distant antimatter stars or galaxies. The universe, as far as we can see, is made almost entirely of matter. To understand why, we must study antimatter directly. A monumental challenge because it annihilates the moment it touches any normal container. The Alpha experiment at CERN has achieved the extraordinary feat of trapping individual atoms of antihydrogen, the antimatter counterpart of hydrogen, using powerful, complex magnetic fields. By holding these atoms stable for minutes or even hours, physicists can probe their properties with exquisite precision, asking a fundamental question. Does antihydrogen absorb and emit light at the exact same frequencies as regular hydrogen? If they find even the tiniest difference, it could point toward the deeper physics that saved the universe from self-destruction. Could there be hidden pockets of antimatter, perhaps drifting undetected in the vast cosmic voids where collisions are so rare that the telltale gamma-ray signature has not yet been observed. Or might the answer lie with the most ghostly of known particles, neutrinos, which may be their own antimatter counterparts, a property that could have triggered the asymmetry in the universe's first moments. This fundamental imbalance, written into the laws of physics, connects directly to the trillions of these nearly massless particles passing through your body every second. Trillions of ghostly particles are streaming through your body at this very moment, a silent cosmic rain you cannot feel. These are neutrinos, nature's most elusive messengers, born in the hearts of stars and the most violent explosions. They carry no electric charge and barely any mass, allowing them to pass through entire planets as if they were not even there. Yet despite their reluctance to interact, they hold profound sway over the fate of the cosmos. To understand them is to learn the universe's most subtle language. They come in three distinct types or flavors: an electron neutrino, a muon neutrino, and a tau neutrino. A single neutrino can spontaneously change from one flavor to another as it travels, a bizarre quantum behavior known as oscillation. This very property was the key to a monumental discovery. For decades, physicists were puzzled by a missing fraction of the electron neutrinos predicted to come from the Sun. The giant Super Kamiok and detector in Japan, a tank filled with 50,000 tons of ultra-pure water, provided the answer. By observing how these solar neutrinos seem to transform into other flavors on their way to Earth, scientists confirmed that neutrinos must have a tiny, non-zero mass, a finding that forced a revision of the standard model of particle physics. These particles are not just passive travelers, they are active participants in stellar death. When a massive star goes supernova, the core collapses into an ultra-dense neutron star. The sheer energy of this collapse is so immense that it is primarily carried away not by light, but by a tremendous burst of neutrinos. In fact, 99% of the supernova's energy escapes in this form, a ghostly sigh that helps drive the explosion itself, blasting the star's outer layers into space. We witnessed this directly in 1987, when detectors on Earth recorded a handful of neutrinos from a supernova in the Large Magellanic Cloud. These ghostly particles arrived hours before the light of the explosion, offering the first tangible proof of their central role in stellar collapse. Today, sophisticated observatories like IceCube at the South Pole are hunting for even more extreme cosmic neutrinos, using a cubic kilometer of deep, clear Antarctic ice as a detector. IceCube looks for the faint blue flashes of light produced on the rare occasion a neutrino collides with an atom. It has detected neutrinos from beyond our galaxy, tracing them back to cosmic powerhouses like blazars, supermassive black holes shooting jets of plasma directly toward Earth. Beyond these cataclysmic events, the entire universe is permeated by a fossil sea of neutrinos, a cosmic neutrino background. This relic radiation was created just 1 second after the Big Bang, a snapshot of the cosmos in its infancy. Detecting this specific low-energy background remains a monumental challenge, but its discovery would provide a direct window into the universe's very first moments, even earlier than the cosmic microwave background. Their influence may extend to the largest structures of all. As the most abundant massive particles in the universe, neutrinos streamed freely in the early cosmos, their slight gravity subtly influencing how matter clumped together to form galaxies and clusters. Their properties are even woven into theories of dark matter. Could there be a fourth, even more elusive type of neutrino? A sterile neutrino that does not interact through any force except gravity. This hypothetical particle is a compelling candidate for the dark matter that binds the cosmos. From the death of stars to the birth of galaxies, these phantoms guide us toward a deeper truth. Their ghostly dance may ultimately lead us to the universe's most fundamental framework, a realm of vibrating strings and hidden dimensions. Our universe might be a three-dimensional island floating in a far vaster, higher-dimensional reality. This is the radical vision of string theory, a framework where the fundamental building blocks of nature are not point-like particles but unimaginably tiny, vibrating loops of energy. The mathematics of this theory demand extra-spatial dimensions, perhaps 6 or 7 of them, all curled up into a space so small that a single atom would be a galaxy in comparison. String theorist Brian Greene often illustrates this by asking us to picture a garden hose. From a distance, it appears as a single line, a one-dimensional object. But up close, we discover it has a circular dimension wrapped around its length. Our universe, he suggests, could possess similar hidden, coiled dimensions at every single point. The specific vibration of each string determines the properties of the particle it becomes, from a massless photon to a heavy quark, offering a potential unified description of all forces and matter. One of the most profound implications involves gravity. In theories with extra dimensions, gravity may appear weak in our world because its fundamental force is actually spread out, or leaking, into these additional spatial realms. Our three-dimensional space could be a membrane, or a brane for short, embedded within a higher dimensional bulk. This idea is central to M-theory, a development of string theory that posits our entire universe exists on a three-brane, with only gravity able to freely traverse the full bulk. This could explain why we are so aware of gravity's large-scale effects, like the shaping of galaxies and voids, while it remains incredibly feeble compared to the other fundamental forces at the particle level. The cosmic voids we have explored might be more than just empty space in this picture. Could they be regions where the geometry of these hidden dimensions is subtly different, allowing gravity to leak away more efficiently and contributing to the accelerated expansion we attribute to dark energy? Or, even more speculatively, might a void be the shadow cast upon our brain by a nearby parallel universe in the bulk, a place with entirely different physical laws? These are untested dreams, but they drive real-world experiments. The Large Hadron Collider has actively searched for signs of these extra dimensions by looking for missing energy in particle collisions, energy that would have carried momentum into a hidden dimension. So far, no such signal has been found, leaving these beautiful ideas in the realm of mathematical speculation. Yet the quest continues, pushing at the very edge of what is testable. If our cosmos is just one membrane among many, what does that say about the unique conditions that allowed life to arise here? And could those conditions be infinitely replicated in a vast multiversal ocean? The profound silence of the cosmos is perhaps its most unsettling feature. With hundreds of billions of stars in our galaxy alone, many hosting worlds in their habitable zones, the universe should be teeming with voices. Yet when we listen, we hear only a vast and unnerving quiet. This is the Fermi paradox, a simple, haunting question. Where is everybody? For decades, scientists at the SETI Institute have been scanning the skies for an answer, using massive radio telescopes like the Allen Telescope Array to sift through the cosmic static for a pattern that screams of artificial origin. They search for biosignatures, chemical imbalances in a planet's atmosphere that could indicate life, and technosignatures, the energy footprints of advanced technology. Jill Tarter, a pioneering figure in this search, has long championed the need for patience, reminding us that we have barely begun to explore the cosmic ocean. The tools are mere buckets, she might say, dipped into a shoreless sea. The famous Drake equation frames this search mathematically, estimating the number of communicative civilizations by considering factors from the rate of star formation to the fraction of planets that develop life, and crucially, the average lifespan of a technological society. It is this last variable that looms largest. Does every civilization that rises eventually face a great filter, a barrier so formidable that it prevents virtually all life from reaching the stars? This filter could be a natural catastrophe, the inherent self-destruction of advanced intelligence, or something we have not yet conceived. Our own cosmic neighborhood offers a potential clue. We reside in a relatively dense part of the galactic suburbs, but consider a civilization born deep within a cosmic void. On an isolated world adrift in that immense darkness, the night sky would be almost perfectly black. The concept of other stars, other suns, might never even arise in their science or mythology. They would be truly alone, their evolutionary path shaped entirely by their profound isolation, perhaps never developing the technologies for interstellar communication we take for granted. This makes the recent discovery of exoplanets in habitable zones, like the 7 Earth-sized worlds orbiting the TRAPPIST-1 star, so compelling. They prove that the ingredients for life are common. But if the ingredients are everywhere, why is the kitchen so silent? Are we, as a technological species, simply an early bloom in a cosmic spring? Or are we one of the last, hearing only the echoes of civilizations that flared and died out long ago? Perhaps they are out there, but using communication methods we cannot yet perceive. Their signals hidden in dimensions of physics we are only beginning to explore. This existential question pushes us to look for life in even the darkest corners of the galaxy, on worlds that have been flung from their solar systems entirely, wandering the cold voids between the stars. These silent wanderers drift through the galaxy's darkest voids, completely untethered from the light of any star. Rogue planets are nomads of the deepest night, worlds that were violently ejected from their home solar systems during the chaotic gravitational dances of their youth. Their numbers are staggering, with estimates suggesting there could be billions, perhaps even trillions, of these dark worlds silently orbiting the galactic center. A hidden population that vastly outnumbers the stars themselves. Detecting something that emits no light and wanders in total blackness is a monumental challenge, but astronomers have a clever tool. They use a phenomenon called gravitational microlensing. When one of these invisible planets passes almost perfectly in front of a distant background star, its gravity acts as a tiny lens, bending the star's light and causing it to momentarily brighten. Surveys like the Optical Gravitational Lensing Experiment, or OGLE, have scanned the crowded star fields toward the galactic center, catching these fleeting flashes. Each one is a ghostly signature, revealing the mass and distance of a world we can never see directly. The formation of these lonely worlds is a story of cosmic violence. In a young, crowded stellar nursery, the gravitational pull of a passing star or a massive planet can easily fling a smaller world out of its orbit, sending it careening into the interstellar void. Some may even form on their own in the cold, collapsing directly from small clouds of gas and dust, never knowing the warmth of a sun. The immediate image is one of a frozen, airless rock, but the reality could be far more intriguing. A rogue planet with a thick hydrogen atmosphere could trap its own internal heat, creating a surface temperature warm enough for liquid water. Others, like icy moons in our own solar system, might harbor vast, global subsurface oceans, kept liquid by geothermal energy from a radioactive core or the gravitational tugging of a captured moon. In these lightless, abyssal seas, life could potentially cling to existence around hydrothermal vents, drawing energy from the planet's interior chemistry rather than from sunlight. The possibility of panspermia adds another layer of wonder. If life did arise on a planet before it was ejected, that life could potentially survive the journey, hibernating in protected niches. These nomadic worlds could then act as interstellar arcs, seeding life across the vast galactic voids. Future telescopes, like the Nancy Grace Roman Space Telescope, are designed with the power to directly image some of these nearby rogue planets by blocking out the light of stars, finally bringing these dark wanderers into focus. Could the most common habitable environments in our galaxy be these lonely, sunless worlds adrift in the eternal night. Their existence forces us to expand our imagination of what a living world can be. This very fabric of space which these planets traverse might itself be vulnerable to forces far stranger than mere emptiness. The very fabric of space we inhabit may be built on a foundation that is only temporarily stable. Our universe could be resting in a false vacuum, a precarious valley in the landscape of reality, with a far deeper chasm of true vacuum lying below. A single, random quantum event anywhere in the cosmos could, in theory, trigger a catastrophic transition. Imagine a bubble of this true vacuum suddenly nucleating, perhaps in the emptiness of a cosmic void. This bubble would then expand in all directions at the speed of light, its wall rewriting the fundamental laws of physics as it passes. The constants we rely on, the forces that hold atoms together, would be permanently altered in an instant. Inside this expanding sphere, reality as we know it would simply cease to exist, replaced by something entirely unknowable and almost certainly inhospitable to any form of life or structure. The physicist Stephen Hawking once reflected on this as the ultimate environmental catastrophe, noting that there is no warning and no defense. It would be an end not with a bang or a whimper, but with a silent, unstoppable rewrite of existence itself. The stability of our world hinges on the behavior of the Higgs field, the energy field that gives particles their mass. The mass of the Higgs boson discovered at CERN places our universe in a potentially metastable state. It is like a ball balanced on the rim of a bowl, seemingly stable but capable of being knocked into a much deeper bowl with far less energy. A process called quantum tunneling could provide that nudge, a random fluctuation that kicks the Higgs field over the energy barrier and into its true lowest state. The terrifying aspect of this scenario is the utter lack of any precursor. One moment the universe is normal, the next, a wall of annihilation is upon us, already moving at light speed. There would be no time to react, no time to even comprehend what is happening. The cosmic voids we have explored, with their incredibly low densities of matter and energy, might be the most likely places for such a transition to begin. In these near-empty regions, the energy barriers could be lower, making the quantum tunneling event slightly more probable. This concept of false vacuum decay is not just a story of cosmic doom. It is also woven into theories of the universe's birth. The inflationary epoch that shaped the cosmos is thought to have begun with a similar transition, a bubble of true vacuum expanding to create our entire observable universe. This suggests that if our cosmos is part of a multiverse, we may simply be one bubble among many, each with its own unique physical laws, and our bubble could one day be erased by another. Could we ever hope to detect signs of this impending catastrophe? The answer is likely no. The event would be instantaneous and complete, offering no observational signature until it was far too late. It remains one of the most speculative and profound existential threats conceivable, a reminder that the laws of nature we take for granted might be nothing more than a local and temporary ordinance. This ultimate fragility of reality stands in stark contrast to the steady, predictable flow of time, a mystery that feels so fundamental yet may be just as illusory. Time itself may be the universe's most fundamental illusion, a persistent arrow pointing from a definite past toward an uncertain future. This one-way flow is not just a feature of our minds, but a property of the cosmos, deeply woven into the increasing disorder we call entropy. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. A shattered glass does not reassemble itself, and smoke never flows back into a cigarette. This thermodynamic arrow of time, the relentless march from order to disorder, is the one we experience most directly. Its origin, however, lies in the deepest past. Cosmologist Sean Carroll explains that the early universe was born in a state of incredibly low entropy. a condition of exquisite and improbable order. This single fact is the reason time has a direction at all. From that smooth, dense beginning, the universe could only evolve in one way, toward higher entropy, creating the possibility for galaxies, stars, planets, and life to form. This increasing disorder is what powers every process, from the nuclear fusion in a star's core to the electrical impulses in your brain that create consciousness itself. We experience this flow psychologically as the arrow of time, our unshakable sense of past, present, and future. This psychological arrow is inextricably linked to the thermodynamic one, as our memories are physical records formed by irreversible processes in our brains. There is also a cosmological arrow of time, defined by the expansion of the universe. As space stretches, galaxies recede from one another, and the cosmic background radiation cools. All these arrows point in the same direction, from the low-entropy Big Bang toward a high-entropy future. Black holes represent the ultimate victory of entropy in our universe. Their event horizons possess an immense amount of disorder, maximizing entropy within a confined volume. This links directly to the holographic principle, a revolutionary idea suggesting that all the information describing the three-dimensional volume of a black hole is actually encoded on its two-dimensional boundary, the event horizon. This concept may extend to the entire cosmos, implying that the information for our reality could be projected from the boundaries of the observable universe. In the vast cosmic voids where matter and energy are so sparse, the local experience of time might be subtly different. With fewer gravitational interactions and physical processes unfolding, the arrow of time remains, but its passage could feel stretched, a slower progression toward maximum disorder in the emptiest places. What happens to time if the universe eventually stops expanding and collapses in a big crunch? In such a hypothetical scenario, some physicists have speculated that the arrow of time might reverse as entropy decreases, with broken glasses reassembling and people living their lives backward. However, all current evidence points away from this dramatic end. The universe's expansion is accelerating, driven by dark energy, leading toward a final state of maximum entropy known as the heat death. In this eternal, frozen future, when all energy is evenly distributed and no more work can be done, the arrow of time may effectively cease to have meaning. With no processes left to drive change, the distinction between past and future could vanish. This profound connection between time, entropy, and the cosmos's structure forces a radical question. Was our universe's incredibly low entropy beginning just a singular, random accident? Or is it a natural consequence of a wider reality where our cosmos is just one bubble in an infinite and eternally shifting multiverse? Our universe might not be a single, solitary creation, but one of countless others in an infinite cosmic ensemble. This is the Multiverse Hypothesis, a radical vision where our entire cosmos is just one bubble in a vast, ever-expanding froth of realities. Cosmologist Andre Linde, a key architect of this idea, describes how eternal inflation naturally gives rise to this scenario. In this picture, the rapid expansion of spacetime that shaped our early universe never truly stops overall. Instead, it halts in localized patches, each one becoming a separate bubble universe with its own unique physics, while the broader inflationary background continues to spawn new bubbles eternally. Our universe, with its specific constants that allow for our existence, would be just one fortunate island in an infinite archipelago of possibilities. This provides a compelling, if speculative, answer to the puzzle of fine-tuning. Why do the fundamental forces and particle masses have the precise values needed for stars, planets, and life to form? In a multiverse, there is no deeper reason. We simply find ourselves in one of the rare bubbles where the conditions are just right. The cosmic voids we have mapped could be more than just emptiness in this picture. They might be the scars of ancient bubble nucleation, the boundaries where our universe first inflated, or even the subtle shadows cast upon our space by adjacent, invisible universes floating in a higher dimensional bulk. Scientists actively search for evidence of such cosmic collisions, looking for unusual patterns or concentric rings in the cosmic microwave background that could be the bruises from a long-ago impact with another universe. Beyond inflationary bubbles, other multiverse concepts emerge from different branches of physics. String theory suggests our reality could be a three-dimensional membrane, or brain, existing alongside others in a higher dimensional space. The many worlds interpretation of quantum mechanics proposes that every quantum decision branches off a new, equally real universe. While these ideas are profoundly different, they all point toward a reality far grander and more strange than we once imagined. The lack of direct proof is a significant challenge, placing the multiverse at the very edge of testable science. Yet the philosophical motivation is powerful, encapsulated by the anthropic principle. The universe appears fine-tuned for life because, in an unimaginably vast multiverse, some universes must be, and we can only exist within one of those. Could the ghostly particles of dark matter be visitors from these neighboring realms, slipping into our universe through hidden connections in the void? The silence of the cosmic voids might be filled with a ghostly sea of particles we have yet to see. Among the most compelling candidates for dark matter is the action, a hypothetical particle born not from the dark matter puzzle itself, but from a deep mystery in the heart of the atom. To understand why physicists conceived of the action, we must look at the strong nuclear force, the glue that holds atomic nuclei together. This force exhibits a puzzling symmetry, known as charge and parity symmetry, or CP symmetry. In simple terms, the equations governing this force should treat particles and their mirror images differently, but in reality they do not. This is the strong CP problem, a nagging inconsistency in our most fundamental theories. The action was proposed as an elegant solution, a new field that would naturally restore this balance, and in doing so, it predicted a very light, very weakly interacting particle. It was a fix for a theoretical problem that unexpectedly produced a perfect dark matter candidate. Unlike the heavier WIMP, or weakly interacting massive particles, actions would be billions of times lighter, behaving less like discrete bullets and more like a pervasive, coherent wave washing through the cosmos. This wave-like nature is key. In the cold of the early universe, a vast number of actions could have pooled together to form a Bose-Einstein condensate, a quantum state where countless particles act as a single, fluid-like entity. This would explain the smooth, non-clumpy distribution of dark matter we observe, especially within the immense cosmic voids, where it forms a gentle, overarching potential that guides the evolution of these empty regions without collapsing into dense knots. How do you hunt for such a phantom? Experiments like the Action Dark Matter Experiment, or ADMX, are essentially the most sensitive radio receivers ever built. They operate on the principle that an action, in the presence of a powerful magnetic field, could very rarely convert into a microwave photon. The experiment uses a tunable resonant cavity submerged in a strong magnet, slowly scanning through millions of potential frequencies, listening for a faint, narrowband whisper of radio waves that would signal the presence of actions of a specific mass. It is a painstaking search for a single, pure note in a universe of cosmic static. The action hypothesis also leads to some wonderfully strange possibilities. This cosmic condensate could, under certain conditions, collapse into self-gravitating objects known as action stars. These would not be stars of fire, but fragile, macroscopic clumps of quantum waves. While they would be nearly invisible, their gravitational influence could be detected if they passed in front of a distant star, briefly bending its light through gravitational lensing in a unique and identifiable way. Other candidates still vie for the title of dark matter. Primordial black holes, theorized to have formed in the dense first moments of the Big Bang, represent another path. And WIMP, though undetected in deep underground experiments so far, are not entirely ruled out. Yet the action's dual role in solving a fundamental particle puzzle and explaining the dark, smooth cosmos gives it a compelling elegance. If these particles are real, their discovery would do more than just identify the universe's missing mass. It would forge a direct link between the quantum rules governing the smallest particles and the grand architecture of the cosmic web, revealing a deeper harmony in the laws of nature. This quest for a particle from the universe's first moments brings us to the cataclysm that may have created it, the dramatic end of the inflationary epoch. The universe was born in a silent, empty chill. For a fleeting fraction of a second, the explosive expansion of inflation had stretched space to an unimaginable smoothness, leaving it cold and devoid of the particles that would become everything we see. This profound stillness had to end, and its end was anything but quiet. The moment inflation ceased, the universe underwent a violent rebirth known as reheating. Cosmologist David Kaiser describes this as a cosmic phase transition, a dramatic shift where the energy locked in the inflattened field, the engine of inflation, was unleashed in a torrent. This was the true beginning of the hot Big Bang, the fiery genesis of the particle world we recognize. The mechanism of this energy transfer is one of cosmology's great puzzles. The leading idea involves the decay of the inflattened field, a process where this primordial energy transformed into the quarks, electrons, and photons that would fill the young cosmos. In some scenarios, this decay did not happen smoothly. A phenomenon called parametric resonance could have occurred, where the oscillating inflattened field pumped energy into specific particle types with explosive efficiency, like a singer shattering a glass with a single, precise note. This period of preheating would have been a chaotic, turbulent era, creating intense inhomogeneities that rippled through the nascent plasma. These fluctuations were the raw material for all future structure, the subtle hills and valleys in density that gravity would later sculpt into the cosmic web of galaxies and the vast, empty voids. The process of thermalization then followed, as this roiling sea of particles collided and interacted, eventually settling into the uniform, searing heat of the early universe. The specifics of reheating are not just academic. They directly connect to the genesis of dark matter. It is possible that the very first dark matter particles, whether they are WIMP or actions, were forged in this primordial inferno, their abundance frozen in place as the universe cooled. This intimate link means that understanding dark matter requires us to look back to this first moment of creation. The search for evidence continues. The most promising clue may be imprinted in the polarization of the cosmic microwave background. Certain patterns, specifically the B-mode polarization we discussed earlier, could carry the faint whisper of gravitational waves generated during the violent turbulence of reheating. These primordial ripples would have traveled unscathed through the ensuing billions of years, and their detection would provide a direct window into this otherwise invisible epoch. Could the great cosmic voids, those deserts of space, hold other relics from this time? Theoretical work suggests that the extreme densities during preheating might have spawned populations of primordial black holes, and these ancient objects could be drifting unseen in the emptiness today. Their gravitational influence would be the only sign of their presence. What if the very structure of the voids themselves, their specific sizes and distributions, are a fossil record of how the inflattened field finally decayed? This foundational event, which set the initial conditions for all of particle physics, pushes our understanding of reality to its absolute limit, suggesting that the information describing our entire cosmic volume might be encoded on its two-dimensional boundary. A black hole's event horizon might be the most information-dense surface in the universe. This startling notion lies at the heart of the holographic principle, a radical idea born from the fiery clash between general relativity and quantum mechanics. It proposes that our three-dimensional reality, with all its depth and volume, could be a holographic projection from a two-dimensional surface at its boundary. All the information needed to describe every star, every planet, and every person within a region of space is somehow encoded on its outer shell, like a cosmic barcode. Theoretical physicist Leonard Susskind, one of the pioneers of this concept, framed it as a way to reconcile the gravitational laws that govern the large with the quantum rules that dictate the small. He explained that holography unifies these domains by describing the universe in one fewer dimension, suggesting that the world is in some sense a projection from a distant, underlying reality. The most concrete, albeit theoretical, example of this is the AD/CFT correspondence. It establishes a perfect mathematical duality between a hypothetical space with negative curvature, known as anti-de Sitter space, and a conformal field theory that lives on its lower dimensional boundary. It is a universe in a can, where the gravity-filled interior is completely described by a quantum theory without gravity on the tin. Our real universe, however, is not anti-de Sitter space. It is expanding and filled with dark energy, making the direct application of this elegant correspondence a monumental challenge for cosmologists. This profound idea directly tackles the black hole information paradox. When matter falls into a black hole, what happens to the information it contained? Quantum mechanics insists this information can never be truly destroyed. Yet general relativity suggests it is lost forever behind the event horizon. The holographic principle offers a breathtaking solution. The information is not lost inside the black hole. Instead, it is meticulously painted onto the event horizon itself, preserved in the intricate microscopic structure of that surface. Any attempt to violate this principle, to force information to be lost, leads to a bizarre and violent contradiction known as the firewall paradox. If an observer falling into a black hole could somehow access information both inside and on the horizon, the very point of crossing would become a wall of blazing energy, a clear sign that our current physical theories are in conflict. Holography smooths out this conflict by stating that the interior and the boundary are not independent. They are two descriptions of the same reality. What does this mean for the vast cosmic voids? These immense regions of near-nothingness could be considered information-poor deserts. The amount of information or entanglement entropy in a region is thought to be related to its area, not its volume. A void, with its incredibly low density of matter and energy, would have a far simpler holographic description than a dense galaxy cluster. Its boundary would encode far less data, representing a cosmic blank slate in the grand hologram. Could the pristine emptiness of these voids provide the cleanest testing ground for these wild ideas? Their simplicity might allow theorists to make clearer predictions about how the holographic principle manifests in a realistic, expanding cosmos like our own. We are left wondering if the ultimate nature of reality is not a rich, three-dimensional tapestry, but a shimmering, two-dimensional projection whose deepest secrets are written at the edges of everything. Our journey into the void reveals a cosmos far grander and more mysterious than we ever dreamed. We have felt the ghostly grip of dark matter shaping the cosmic web, and witnessed the silent, relentless push of dark energy stretching the very fabric of space. We have stood at the precipice of black holes, where time itself seems to stall, and marveled at the impossible density of neutron stars. From the tiniest quantum seeds sown in the first instant of inflation to the staggering possibility of a multiverse, each mystery pulls back another layer, revealing not just emptiness, but a dynamic stage for the universe's greatest dramas. These encounters do not diminish our place in the cosmos, they enrich it. They remind us that science is our most powerful lens for revealing the unknown, a never-ending story written in the language of mathematics and observation. The next time you gaze at the night sky, let your eyes linger on the dark spaces between the stars. See them not as voids, but as realms of profound potential, holding secrets that future generations will strive to uncover. We would love to hear which of these tales resonated most with you. Share your thoughts in the comments, and if you are eager for more journeys to the edge of understanding, be sure to subscribe. The universe is a story still being written, and its greatest chapters are waiting in the stars.